Thank you very much. Niels, time to sit down. You, grab a seat. Amos. Connor, Amos, there you go. Patrick Holmes, are you here? Okay, you're going to go right after Farzad. Okay, so we're going to, the third talk is canceled. All right, just so you know. So just a reminder for the speakers to bring up their computer when we're in the question period so we can move over quickly and change microphones and so on. A couple announcements. There is Wi-Fi here. Many of you probably have discovered it, but there's an open network called DWC 2018. And I'm going to forget at the end, so I'll say it now. There is also coffee just upstairs. So, and nobody used it. So in the coffee breaks, if you go upstairs, you'll find a second set. All right. Everybody ready?
Yes.
All right. This is the balance and stability section. I am still Max Donnellan. And this is Hendrik Reimann coming from the University of Delaware. And I'll let you introduce your talk.
Thank you. Yeah. Okay. So we heard a lot about metabolic efficiency, or efficiency of walking. But you can't be efficient if you're not walking, and you're not walking if you fall. So this is all about how to prevent that. And what we're looking at is, just speed through the figures. What we're looking at is the role of vision for that. It seems to be a bit dark. I just wanted to give you an idea of what we do experimentally to understand how humans prevent themselves falling over while they're walking. We have them walk in a VR setup, and then we mess with them by changing the world around them. Okay. So we kind of probe the role of the visual system for the control of balance during walking. And we look at a bunch of things. What exactly I'll go through and hopefully let you know how people do that. So this is just slow motion of the same thing. Just a brief overview of our setup. We have this beautiful VR cave that covers almost your whole field of vision. And then we market people up, have them on a self-paced treadmill so they can walk at their own speed. And this is the scene that we use, which kind of gives you the right depth information. And it's pretty compelling. And then they walk, and triggered on heel strike, we use visual stimulation to give them the impression that they're falling. It's always triggered on heel strike, but can go in either direction, left or that they think they're falling either left or right. And we have data from 20 healthy young people, and the data is somewhat involved, so I kind of misplaced the pointer. Just let me run through what we see here. So this is an overview of what happens. The scene rotates, and it stays rotate for a while, and then it rotates back. And we look at the first 4-step, so this is 4 steps, and this is what their center of mass does. Well, the color code is always going to be the same. If they think they're falling to the left, it's going to be blue. And what happens here is that their center of mass then shifts a few centimeters to the right during the first 4 steps. So pretty much this tells you the stimulation works. They actually do think their balance is threatened, and they correct accordingly. And what we're looking for is, how do they generate that specifically? Next.
So when you say it rotates to a fixed angle and stays at that angle, or it just keeps rotating for that period and then?
So it's an accelerating rotation, mimicking the acceleration of gravity, and that keeps accelerating for 600 milliseconds. Then it reaches about 10 degrees rotation, and it stays there. Because if it keeps rotating, it's just too much. Yeah. But we're mostly looking at what happens in this initial period, where it's a kind of normal fall stimulus that you also. Yeah. Okay. So our question is, how do you generate? This is a corrective response. You think you're falling to the left, so you push your center of mass to the right. And how specifically do we do that? And everybody knows about kind of the role of foot placement, but we were interested in if that's really all that humans do, if that is enough. Yeah. So turns out it's not. Bit of a spoiler. Well, that's not all that humans do. The first thing we look at is what we call the ankle roll mechanism. So one thing you can do is in single stance is you have one leg on the ground and you can kind of use your ankle musculature to pull on that leg or pull your upper body along the leg, and that also rotates the foot segment on the ground and shifts your center of pressure. And what we see there is data from 3 variables now, all relevant to that mechanism. So what you have here is the center of pressure relative to the center of mass, and the lateral angle of the ankle joint, and the neuronal or the activation, the EMG of a relevant muscle. And this is data from the first step. You have double stance period here, and this is where the perturbation starts, and then swing of single stance. And what you see is that nothing happens for a while. That is for about 300 milliseconds. And then the center of pressure systematically starts changing in the direction where you think you're falling. And the angle also changes, and that goes along with a change of the relevant muscle activity. You activate your muscle more or less depending on which direction you want to pull. So that's pretty good evidence that the first thing that people do after they think they're falling is actually to modulate their single stance and not wait until they get to place the next step, which is something they also do. So this is kind of the big mechanism that everybody looks at mostly, which in a way, which is relevant to robotics, is already enough to control a walking thing. So I'll kind of go through this briefly. This is the position of the heel medial-laterally. Here I added like a double stance towards the end. So you have double stance, then single stance, and then another double stance. And you see that towards the end of the single stance, they shift their stance, their swing foot in space, also in the direction where they think they're falling. But the funny thing is, talking about falling, the funny thing that we discovered here, so again here you have the kind of kinematics, where your foot is, and then a joint angle, which is the swing leg hip abduction. And then you also have the muscle activity that generates that abduction. And we were expecting a similar picture as for the ankle, but we didn't find it. We did not really find a noteworthy abduction change or EMG activity. So we were really puzzled because what generates this swing foot placement? And we haven't completely nailed it down yet, but so this is just to say, even the little change that is there in the abduction doesn't really add up in time because it comes too late. And we looked at other variables, and what we found, what might explain that, is when you look at the internal, external rotation angles of the stance leg knee and the swing leg hip. And I won't go through this in detail, but these two rotate internally, externally, that together they create a kind of a lateral shift of your swing foot. So yes, foot placement happens, but it's a lot more complicated in humans than what you would expect. And then another thing was that kind of fell out of this that we're pretty excited about is we looked at all the angles, and one thing that jumped at us is we looked at the plantar dorsiflexion angle of the trailing leg as you get through a double stance. And we see a pretty strong and systematic response. And the way we understand what we think happens here is that you modulate your push-off force. And what's happening is that if you think you're falling to the left, then with your left trailing foot, you push off more. So I think I'm falling to that side, and I'm in kind of this position. So I push off, and that pushes me mostly to the front, but also a little bit to the right. And that's how we currently explain. You use this as a balancing mechanism to also accelerate your center of mass medial-laterally. And just stick figure a bit of what I just explained. So if you push it's like weight shifting between your two stance feet. So if you shift weight between your feet, you mostly shift in the anterior direction, but also a little bit to the side, which is probably what you want. That's already it. If you want to know more about this, we have a poster up. Tyler presents that. Find the poster and we can talk about this at length.
Videos, the minute of information, the hands sort of play them out.
Yes, we do have data for that. We have a lot of data, and there's limited time. We have several times been talking about, but we have not really concretely looked at that. Yes? Yes.
So do any of them have like the initial reaction which is like closer? And this is the light.
No. So the thing is, they're walking on a treadmill, and you can't walk on a treadmill when you close your eyes. You just drift off to the side. You might be able for a minute or two, but you cannot stable state walk on the treadmill. Even though it's self-paced and will keep you from walking off in the front and back, after a few steps, you'll just hit the sides. So that's not a good strategy. Thanks.
So a related question, in your study you have essentially a conflict between vision and precipitous. And I'm assuming you're doing multiple perturbations for each person.
Yes.
So do you see adaptation of the perturbation response? And if so, what tends to change first? Is it the center of pressure? Is it the foot placement, or do they change simultaneously?
So the question is whether there's adaptation over time. We do see a bit of an adaptation effect. It's very fast. It disappears after a few. So we run. It's a long study. It's like almost an hour of walking, and adaptation disappears after about the first half dozen perturbations, and we understand it more as a startling effect. So when people get this the first time, they're like, whoa, what's going on? But then very soon they these are healthy young people, they just shrug it off more or less and go ahead.
Mr. Slack.
Yeah, I've got two questions from Slack. The first one is, how do you control for perturbing right at the heel strike?
We have a marker on the heel, and we use a simple threshold. So we set that threshold depending on where the marker is, and when we track the state, track between swing and heel. So we detect heel strike by a downward crossing of that marker. Yeah.
Okay, and the second question is, are there any differences between terrains? Would, for example, sand prevent push-off?
It might. We can't really put sand on our treadmill in any meaningful way, so we have a hard time testing that. But yes, that's actually a direction that we're planning to go into, to see how terrain is hard to test, but how different factors might modulate which one of these mechanisms you use, how you coordinate. Also looking at patient populations, there are people who have particular trouble with modulating their push-off force, but that's future work. Yes. So we looked at, not really momentum, we looked at angle changes, and there are things going on. They're a bit more complex and not really not really relevant for this. So their head rolls a bit in the direction of the horizon, so follow the horizon. If I remember correctly, it's been a while since I looked at that, their upper body kind of rolls in the opposite direction, actually. We can talk about that later, so I'm not 100% sure about that.
Okay. We still have time for a couple more questions.
Okay.
Can you hear me? Yeah, sorry if I missed this, but did you So how do you think the mismatch between the, let's say, vision and the vestibular system plays into how the person responds to the perturbation?
I don't know. That's a great question. So we also use vestibular perturbations. We also run that, and we see very similar things. So we do, both of these play a role and give you information about similar things, and there is something going on in the brain that fuses these two sensory modes. We don't know how exactly that happens. Would be very excited to find out, but I think that's a very tricky question.
Thank you. During your talk, I seem to have picked up on something that apparently surprised you, that it was an effect that wasn't what you expected and it happened too late. I wonder if you might expand on your insight or speculations on that.
Yeah, so that was about the foot placement mechanism. So people know there are different mechanisms of how you can balance a locomoting system like that. Main mechanism people look at is the foot placement, where you shift your foot placement in the direction of the fall to balance. And everywhere we looked at, the kind of mechanical way to do that is to change your hip abduction angle, which often when you build a robot, that's pretty much the only degree of freedom that allows that. So that is kind of what we expected to see. That we would see, like we did see a clear change of the foot placement, but we did not see a change in hip abduction angle to go along with that. So yes, the foot placement was changed, but the biomechanical mechanism to generate that was much more complex. And we haven't really nailed this down yet, but the very likely candidate is that you have a combination of internal, external rotations of the knee, stance leg knee, and swing leg hip, which are degrees of freedom that robots don't have. But humans have them, and they actually do use them. So it's a kind of complicated rotation of the stance leg, pelvis, and swing leg that then has the net effect of translating your swing foot.
Okay, great. Let's thank Hendrik one more time.